So first, we are going to introduce decision trees for regression. The data set that I chose is a data set of measurements of Playboy playmates. So these are girls who are featured in this Playboy magazine. Now, I chose this data set because, of course, it doesn't really make a lot of sense to predict the cup size or the waist or hip size, whatever, based on other measurements. So there is no practical meaning in that. But I chose this because it is very easy to understand what's going on, and it is very easy to see if decision trees make predictions consistent with common sense, right? And since decision trees are very interpretable algorithm, so I think it's the best thing to do. Okay, so now I removed incomplete records here, and the total number of records in the training data is 160. So if we look at some plots, so over the years, the BMI, body mass index, seems to have a decreasing trend. Then hip size remains more or less the same over the years, so in Playboy magazine. Now, we will try to predict a playmate's BMI, body mass index, from height and hip size, right? So here is the scatter plot. So notice that, well, body mass index is something I remember that it's something like height divided by squared mass, something like this, or squared height divided by mass. But it has to do with height and mass, height and weight, right? So, and of course, it's going to increase as the height decreases, right? So it's going to increase from left to right. So from right to left, body mass index is going to increase, and body mass index is going to increase if the hip size is increasing, right? Because the hip size increasing means that the weight is also increasing. So the hip size from bottom to top, body mass index is also going to increase. And this is what we see here. So we see bigger dots on top, smaller dots on bottom, bigger dots on the left, and smaller dots on the right. So here is our decision tree. So it makes its predictions by splitting the data. And now let me first demonstrate how we can construct a prediction for some specific new observation. So let's say that hip size is 35. Yeah, this is American data set, so all measurements are in inches. So this means 35 inches. And height is 68. Again, this is inches. So initially we are here in the so-called root, and this is called the root, just like in discrete mathematics. So this is the root of a tree. And the root is about hip size, right? So the question here that we are going to ask for our new observation is whether the hip size is smaller than 35.25 or not smaller, right? So if it is strictly smaller, we go to the left. So yes is on the left. If it is bigger than or equal than 35.25, we go to the right. So in our case, hip size is 35, so which means it is strictly smaller, right? So we go to the left. So now we look at the height. And our height is 68. So, and the question and the next node is height bigger than or equal than 65.75? And our height, 68, is bigger. So the answer is yes. And if the answer is yes, we go to the left. Okay, so the next thing is we look at the hip size again. And the hip size is 35. And the question is whether the hip size is less than 34.75, and the answer is no, right? So, and since the answer is no, we go to the right, and here we came to the end, right? So these nodes are those nodes where the tree makes its prediction. They are sometimes called leaves, or sometimes they're called terminal nodes. And sometimes we will call them decision regions, so regions. I will explain why regions in a few minutes, in a couple of minutes. But now, what does it tell us? So it tells us that the prediction here is, well, somehow they these two numbers are just coincidentally the same. So 18.12, but this is just a coincidence. So this number 18.12 is our prediction, right? So this is our prediction for the decision tree. So prediction is 18.12. So this is our prediction. So the other 18.12% means that if you look at all our training data, then if you apply this process to every observation in the training data, then 18.12% of all the training observations will be classified by this node. So 80.12% of training data sits here. And so on, right? So, you know, like in this node, if you apply, contains 6.25% of all the training observation, right? So if you apply this process to all the training observations, then 6.25% of everything is going to end up in this node, and so on. Now, the number that is written on each node is the prediction, and that prediction is simply the mean value of our body mass index for all observations that of all training observations that are belong to that node, right? So this is how it works. Now, these are decision boundaries, right? So this means the following. Yeah, so we are in, so let's say our observation is hips 35, height 68, right? So hips 35 is somewhere, this is 32, 36, so hips 35 is probably 32, 33, 33. No, stop. It's a bit hard. So probably 33, 33, 34, 35. 34, 35. So 35 is somewhere here, right? 35 and 68. 68 is, I guess, somewhere here. So our training observation is somewhere here, right? So it probably belongs to this region, I guess. It's a bit hard to see. But let's say this is our observation, right? So hips is 35 and height is 68. Now, this is the new observation. At the same time, there are some training observations that are somehow scattered here. So there are 160 of them, right? So what decision tree does, it figures out which of these decision regions the new observation belongs to, right? And once it is identified, so the prediction here is going to be just the mean or the average value of all the training observations that live in that region, right? So from this point of view, it is very, very similar to k nearest neighbors. So only in k nearest neighbors, so the neighborhoods that we use for predictions, they overlap. But here, these regions, they do not overlap. So every new observation is classified to precisely one of these regions. And this makes this decision tree so easy to interpret, unlike k nearest neighbors. So if you plot the graph of prediction of a decision tree, then you will see this piecewise constant. So, and it's going to be a collection of rectangular regions, and on each region, the prediction is a constant, right? So because on each decision region, the prediction of all the new observations that would be classified to that decision region is just the average of all training observations that belong to that decision region. Okay, so this is how a decision tree makes its prediction. So now please do the first quiz.